Hi, I'm going to go through the video solution for this. I didn't do too many bells and whistles. I'm just going to talk over it while writing on explain everything. So if you need more visuals or having trouble like picturing what I'm talking about as I'm just writing over the surface, please reach out on Google Chat and we'll go through it in more detail. See you later. All right, so in this problem, we got all kinds of data that we need to pick out of that paragraph and just kind of going through that quickly. We have an area that's going to come back that we'll need as part of a formula. They give us this thickness here, but it doesn't actually quite matter because they give us all the other ones down in the table below. So I don't need to write down this thickness because it's down here already. But other things I want to pay attention to is this temperature difference from the ice down to the hot plate is 100 degrees Celsius. That's going to be ultimately what we call our delta T. That's 100 degrees Celsius, and that's from the hot reservoir down to the cold reservoir. That's the change in temperature of how those two materials compare. So also, let me just write down the area while we had it. Area was 0.025 meters squared. So we'll come back to those as we get started, but as we keep reading, then they have this Q over T concept graphed, and they graph it versus length, or at least they're recording those values down. And they say, what should we graph in order to come up with a linear slope? So over in the next section, just kind of minimize this then off to the side, and bring this one up. In the next section, they want us to plot something that would yield a straight line. So if you go over to your toolkit, you're going to have an equation it's pretty much spelled out for you that Q over T, which is in joules per second, if you graph that versus, well, if you just look at the formula, it says Q over T equals Ka delta T over L. So, I mean, if I graphed Q versus delta T or Q versus A, that would give me a direct relationship. These students graphed length, or at least have length in their data table. So if I were to just graph off the numbers that they had, I'd get an inverse graph. So I don't actually want an inverse graph. I want to graph, well, let me go back up to the actual graph now. So I want to graph Q versus T versus 1 over L in 1 over meters. That way, it'll show up as a straight line. So in that equation, I'll go back to that one more time. Q over T equals Ka delta T. Now I'm just going to say times 1 over L. Now it's in the form of like Y equals M times X. All of this will be my slope. So K times A times delta T will be my slope, and my X-axis will be 1 over L. All right, so I'm done with part 1. I've labeled it and got my units. Then in part 2, they want me to scale this out. So I have to go back over here and kind of fill out my values. So if I graph 1 over thickness, basically 1 over L, I'm going to have data points like 100, 50, 33.3, let's this be 25, and then 20. So that would finish out my data table. And then we'll go back and, yikes, sorry, I'll get all these kind of set here. So then you can plot that and just have your major tick marks go by 20. And do that on both axes. And I'll take more time, but you should just plot those out carefully and then draw in your linear fit. So transfer those data points right onto your graph and then plot your line. All right, next in part 3, they want you to use the graph to calculate the thermal conductivity of the plastic. So once again, in your formula that you have over here, it says that Q over T, the y-axis, is equal to all this slope, thermal conductivity times area times delta T times 1 over L. So if you just solve for your slope, you have area and delta T already from what we did earlier. Keep in mind that was up here with 100 degrees Celsius and 0.025 meters. So, sorry, I keep changing the ratio on this. It's messing it up. Close enough. So, let's just go ahead and set that up and solve. You got your slope of your line up here, which should be, should come out to like 1 joule meter per second would be how the slope units would work out. And so from there, you can say the slope should equal all of this stuff here, right? So 1 should equal all of that. So I just set up that formula and say 1 equals K times 0.025 times 100, or 1 equals K times 2.5. So K equals 0.4 joules over seconds times meters times degrees Celsius. It's a big weird unit on that thing, but that's what you would get for your K value. All right, in part B, they want you to start going through experimental errors that might change the thermal conductivity value from what the ideal scenario would be, and you have to be specific. You can't just say like human error is going to cause it. You have to say what it would actually do. So if you go back, let's mess that up again. If we go back up to here and just kind of think through this idea, well, you didn't account for the air around this slab of ice. And so a couple different things that could happen here. There's air all around this ice that's also able to transfer thermal energy to it. And so let's say that these numbers that you had for energy flow rate, if they didn't account for what was actually coming, like if these total values were actually because of the air plus the plastic transferring energy, these numbers are all going to be inflated a little bit because they're including some transfer that happened from the air. So you're getting additional heat flow in, making these numbers higher than they would be if you just looked at the plastic. And in that case, your slope would be a little bit higher. Your K value that you calculate is going to come out higher because you didn't account for the air. On the flip side, if you talk about the heat that's supposed to be transferring straight through the ice, but then escaping out to the air, then we're not actually getting as high of a number as we should. So now, kind of ignoring that first effect I said, let's just imagine that the heat coming through here is not perfectly transferred, but instead gets sent out to the sides, to the air. Then these numbers are going to be less than what they should be because we're not getting the perfect flow rate transfer. So in that case, we'd have a lower K value. But as long as we picked one and then tried to explain it, we should be good. All right, part C should be a no-brainer as far as which way the heat is flowing. And all you got to do is draw an arrow up. I've seen people just kind of get psyched out, though, and they think, maybe it's to the side, or maybe I have to draw it down. But no, the heat is going from the hot plate up to the ice, always from hot to cold, and just kind of have that mnemonic in mind. It's always from hot to cold. You don't transfer the other direction. Like when you say, like, you're letting the cold air in, well, no, you're actually letting the hot air out. It always goes from hot to cold. So that is, I think, it for those sections. Let me get down to the next part D and E. So in part D, they say, describe this at a microscopic level. Well, you have this hot plate that's going to be wiggling its atoms very, very quickly. So they're just vibrating back and forth very, very fast. And then that piece of plastic, okay, right at that interface here, these fast-moving particles from the hot plate are going to be bouncing into the particles of plastic, and that starts to excite them and get them moving faster and faster and faster. Then they bounce into the particles on top of them. And it's this chain reaction that just kind of keeps transferring from one to the other all the way up through that. And that's how it's able to propagate and move, transfer that thermal energy up through the plastic to the ice that's sitting up above. The last one says an extra plastic slab sits on a wood surface. Why is it that the wood feels warm and the plastic feels cold? Well, we actually did this with we had some wooden dowels and metal dowels, and they felt different based on their thermal conductivity. So, that's not metal. Metal. Metal would have a very high thermal conductivity, and wood would have a very small thermal conductivity. So therefore, when you touch it, the metal transfers heat away from your hand much, much quicker. And so it would be transferring heat from your hand transferred into that metal at a higher rate than what the wood would be doing, and that's why it feels cold or feels warm to the touch. The one that's transferring heat away from your hand faster, the metal, is going to feel colder to the touch because it's taking that heat away from your hand, whereas the wood feels warmer because it's not taking as long to transfer that heat away. And that's it. That's the end of the 2019 free response section. If you have other questions, please reach out on Google Chat.